Hi everyone, this is your, it's getting increasingly hard to find a quiet space in the house because everyone else is here. Physical chemistry instructor, Dr. Hopkins. And so what we're doing here is the last of our multi-electron atoms discussion material. So it's the fourth video in that. And this is the last of the material for our second exam. Okay, so we've learned how to write an anti-symmetrized wave function in terms of Slater determinants, and so that represents the electronic state of the atom. But there's another way to describe it. It's much easier than having to write out. If you want to know, hey, we've got this. What's the electronic state? Write out a 70 by 70 Slater determinant. It can get a little tedious. We use what are called term symbols. This is something you might have learned if you had advanced inorganic. But basically, the term symbols are we're building on the electronic configurations to describe and then we can describe the energy of the electronic states from these term symbols. Okay, so a term symbol is basically in the center of this screen. We have 2s plus 1, L, and J. The 2s plus 1, and I'm skipping the order. 2s plus 1 is what we call the multiplicity, where S is our total spin angular momentum. So if we summed all the electrons in the atom and then added up what their spin angular momentum was, that's what S is. And then multiplicity is the 2s plus 1 term. So if that term is 1, it's what we call a singlet. 2 is a doublet, 3 is a triplet, and on and on and on. The L term in there is the total orbital angular momentum. So that's when we put the electrons in the m sub L states of our various orbitals. If we sum all of those together, that's what that angular momentum is. And so we use the same kind of notation that we use for atomic orbitals, except we use capital letters. But once again, if the capital L, the total orbital angular momentum, is 0, we call it S. It's an S state. If it's 1, it's P, and on and on and on. I think there's H, I. There's usually not a J, because I think J is one of the symbols in the actual term symbol itself. And then J is our total angular momentum and is based on the L and S for the system, and it can range, so you can have multiple J's for a given set of a given term L and S, and it can range from L plus S minus 1 all the way down to L minus S. Okay, so you have a number of those. All right, so let's look at an example of one. So if we have a completely filled shell, like a NP6 or an NS2, say like helium had a completely filled shell, where the next electron goes into the next electron shell, so to speak. That term symbol is always singlet S0. So the singlet means we have an S0. The S means we have an L0, and then the only combination of L and S is J equals 0. Okay, so in the L case, that means all of the electrons are occupying the m sub L such that they all sum to 0, and that the S equals 0 indicates that everything is a paired spin, right? So we have no unpaired electrons. So if we look at, say, let's take another example, the ground state of lithium has a term symbol doublet S1/2. So what are our S, L, and J? Well, our S, so the 2s plus 1 is 2, so that means S must be 1/2, right? The only way to get that is to have 1/2. The L is 0 because we have a term set, the symbol is S, and then the J is just the number 1/2, as we show here. And we can try another example. So let's say take the ground state of cobalt and determine the S, L, and J from those term symbols. And you can see we have a quartet F 9/2. So if we look at this, so F, we'll go ahead and assign the L first. The L is equal to 3, because that's by definition. J is 9/2. We could back out what the S is from adding those together, but we don't really know because there's multiple L plus S, J terms, excuse me. So we go back and we look at the 2s plus 1, it's equal to 4. The only way we can do that is if S must be 3/2. So we have 3/2, 3, and 9/2 as our terms. So you should, at this point, be able to at least understand how to read what's the S, what's the L, what's the J for a particular term symbol. Now, how do we use them? Now, this is the energies of 2s plus 1 L sub J states follow what are called Hund's rules. And then this is something we used in general chemistry, but we're going to elaborate on it because it's applying to these actual term symbol states. So basically, if you have the first things first, you look for whatever has the greater spin multiplicity is lowest in energy. So whatever has the highest 2s plus 1, it's lower in energy. So the less paired electrons you have, the lower energy it has. And then if something has the same spin multiplicity, then it's the larger orbital angular momentum, so the larger L value that has lower in energy. Okay, now this last part, these last 2, 3, and 4 are a little trickier. So if your unfilled your unfilled orbital, so if you're in a p state, if your unfilled is greater than or equal to half. So if we had in a p state, if we have p equals 3, 4, 5, or 6, then the highest J, higher J, is lower energy. If the unfilled orbital is less than half full, right? So if we're using our example of the p orbitals, if we have p1 or p2, then the lower J is the lower energy. Okay, so table 11.3 in your book, page 264, shows all of our possible for 2s plus 1 L states for, actually, I don't know if it's for every single possible electronic configuration, but it shows for many of them. And you'll notice if you look that up at this point, the NP1, so for 2P1 or 3P1 or whatever it might be, the term symbol or the 2s plus 1 L is doublet P, and then we're gonna determine the allowed J values and figure out which one's the lowest in energy. And in the NP1, there's only one term symbol for that one. So if you look in that table, that only has one. If you look at some of the other electronic configurations, they have many of these term symbols. All right, so what are the allowed J values? So what's our S? Our S is a doublet, so it's 1/2, and our P is 1, right? So, or an L equals 1, so L plus 1/2, so 1 plus 1/2 is 3/2, and then L minus, so then subtracting 1 from that is 1/2. That's the lowest we can get. So we can get J equals 3/2 or 1/2, or in other words, we'll get one of these two symbols, a doublet P 3/2 and a doublet P 1/2. Now in this case, our orbital is less than half full, so the lower J, 1/2, is the lowest energy. So that's the lowest energy in this case. So why don't you use table 11.3 and practice, write out all the term symbols for NP3. So this is a little bit more complicated because we have multiple 2s plus 1 L's. That's what table 11.3 gives you. And so write all of the possible J's for each one of those, and then among all of those, specify which is the lowest. Okay? And so I will leave this for any of our Zoom discussions later on. And I do have a note. Now, maybe from inorganic chemistry, you remember assigning these. I mean, we're going to just use table 11.3 to produce them. We're not going to worry about being able to add up all of the M sub L's and M sub S's in particular in order to understand which particular 2s plus 1 L states are involved with which electronic configurations. We'll just use the table. I just want you to be able to read these term symbols and understand what they mean. All right, so the last topic, and it's very brief because there are a number of atoms on the periodic table, and they all differ in terms of their number of states. As you can imagine, based on table 11.3, the number of 2s plus 1 L states involved for some configurations. So we're going to talk a little bit about atomic spectroscopy. And just so you know, atomic spectral lines are very sharp because there's very little heterogeneous line broadening. So you can still get uncertainty line broadening, and you can still get Doppler line broadening, but you won't get any of that kind of heterogeneous line broadening. So AA, atomic absorption, atomic emission transitions, typically you don't scan a spectrum for those, but they're very, very narrow. And then the selection rules for atomic spectroscopy, the transitions are allowed if delta S is equal to 0. So you can't have a change in spin state. Delta L equal to 0 or plus or minus 1. So you can have a change in orbital angular momentum, but you don't have to. And then delta J is equal to 0 plus or minus 1. And those are basically our selection rules. All right, so that is the end of this unit. And we will move on to molecules next.